It is part 2 of section 1.2. We'll begin with determinants. Let's see this definition. Now, for square matrices, the determinants are scalar value, and we are using the notation DTA, or A, absolute value. When n equal 1, so it's a 1 by 1 metric and having one entry. For the metric, here determinant of A is A, the entry. Now for n equal 2, the determinant is now AD minus BC. Before defining determinants for general n, we'll try to solve this problem. A is given 2103, and we consider linear transformation T. Here Tx is Ax, just metric multiplication. Now find the determinant of A. Okay, determinant of A is quite easily, we can get 6 minus 0, so that is a 6. Right? Determine the image of rectangle, 0, 2, and 0, 1 on the T. Okay, let's try to get image of the rectangle. The original rectangle is given here, and now height is 1, and length is now 2, and 2 and 1. Okay, this position is x equals 2, y equals 0. That position is now x equals 2 and y equals 1. And this one is x is 0 and y equals 1, right? And there is 0, 0. Okay. Now here, on the T, we'll try to get the image, okay? And it's a linear map, so that line will go to line over there. So that if we know the image of this corner point, then we can get the image of the rectangle. Okay, this is R right now. Okay, here 0, 0 will go to 0, 0. Now how about 2, 0? A is now 2, 1, 0, and 3. And here image of this point will be same as now 4 and 0. Okay, so that's 4. It's now image of this point. How about this point? So the same metric, and we have here 2 and 1. Then that will be, okay, 2, 1, and that is 4 plus 1 is 5, and 2 and 1, that is 3. So that here now 5, and that is height is 3. So that this position is 5, and this is image of this point. Okay. How about now the last point here, 0 and 1, the same metric, and x is 0, y equals 1. Then the second column of that 1 is 1 and 3. Okay, so x is 1, y equals 3. So here, that is 1, and this is the image of that point. So eventually, the image of rectangle is given in this parallelogram. Okay, we found that. And find the area of the image. Here, bottom length is 4, height is 3, so that area must be 12, right? Okay, figure out how determinant of A, which is 6, and the area of the rectangle, and original rectangle, that is 2, and the area of the image here, that is now 12. Okay, so we want to figure out how they are related. So the area of original rectangle is 2, and now determinant A is 6, and now area of the image is 12. So it looks like now this 2 multiplication becomes 12. So here the determinant is a kind of a area scaling factor. In general, for general n by n matrices, the determinant can be viewed as the volume scaling factor. And sometimes the determinants are negative, then that is a sort of the negative orientation, some orientation change, but its absolute value is the volume scaling factor. For example, here the determinant A is, for example, -x, then, and now the point is running this orientation, then now because it's 6, again, the point is running same orientation, but it's negative, then the point will run with the other orientation. So the sign is only orientation problem, and if we focus on area, then exactly the determinant is the area scaling factor. For general dimensions is a volume scaling factor. Okay. Now for general n, here determinant can be defined along with a cofactor. Aij is the submatrix of A obtained by deleting row I and column j of A. So that for ij component, we eliminate ith row and j's column, and the submatrix is defined. Okay, let's try to make a picture for that. Here, and summation Aij is given here. Then the row including Aij, column including Aij are eliminated. Then here remaining part will be n-1 by n-1 matrix. That is called Aij submatrix. And cofactor is defined in this way. For the Aij, now submatrix, and we try to get determinant, and -1 to the I plus j. That is Ij cofactor. Now, for general n, here determinant of n by n matrix can be defined in this way. Determinant of A is A11 and the corresponding cofactor plus A12 times the corresponding cofactor of A12 and so on. So that this expansion, cofactor expansion, is done along with, first along with A11, A12, A13, and so on. So that by using first row, the expansion is made. But this cofactor expansion can be made for any row or any column. So also you are making cofactor expansion down the column J, then you can write in this way. Then in any case, the result will be the same as the determinant of A. Okay? Okay, we'll skip the example, and here we have eigenvectors and eigenvalues. For square matrix A, an eigenvector of A is a non-zero vector x such that here now ax equal lambda x for some scalar value lambda. In this case, lambda is an eigenvalue and x is the corresponding eigenvector. Of course, here eigenvector must be non-zero. Once x is 0, then for arbitrary lambda it is always satisfied, so that zero vectors are excluded from eigenvector. Also, once x is eigenvector, then now if we multiply here c, then again Cx is eigenvector. Right? So that for scaling, except the scaling part, the eigenvector is unique. However, here by scaling by C, of course C is non-zero, and you can have some different eigenvector. However, if you consider the direction, then it is unique. Right? Now, the scalar equation, determinant of A minus lambda r equals 0 is called the characteristic equation of A. The polynomial p lambda, determinant of A minus A lambda I, is called the characteristic polynomial of A. The solution of this characteristic equation are eigenvalues of A. To find the eigenvalues of A, we have to solve this characteristic equation. Okay? You can solve this problem yourself. After finding eigenvalues, now you can find corresponding eigenvectors. Okay. Now for n by n matrix, the characteristic polynomial can be written in this way. P lambda is determinant of A minus lambda I. That is now minus 1 to the n, and it's polynomial of n, and lambda n, and some coefficients, and lambda n minus 1, and so on. So the characteristic polynomial can be written in this way, and along with, once it is solved, any polynomial, non-constant polynomial, can be factored into linear factors if we allow this lambda I being complex values, so that this can be written in this way. Here, lambda i's are eigen values. Okay. Here, and so it's a general complex value eigenvalues now. And here, once lambda is 0, then it becomes determinant of A. So here, lambda is 0, then this term can be written in this way. Minus 1 appears n times. Here again, n times, so that minus 1, 2n times, which is 1, so we can ignore, and the remainder part is now lambda I product. This equation means that determinant of A is the product of all eigenvalues of A. So for invertible matrices, determinant cannot be 0. That is the same as eigenvalue. Any of our eigenvalues cannot be 0. Okay. Here we have R vectors, V1 to VR, are eigenvectors that correspond to distinct eigenvalues, lambda 1 to lambda R, of a square matrix A, so that V1 is eigenvector of lambda 1, V2 is eigenvector of lambda 2, and so on. Now we assume these eigenvalues are all different. Then this set must be linearly independent. So here we have a proof. If you are interested in the proof, then try to read it here. Okay, here we define norms, vector and metric norms. Okay, a norm is a function, and we are using this notation, double here, the bar, And now, but this function should satisfy these three conditions. Now for non-zero vector, the function value must be positive. And once lambda is multiplied for the vector, then lambda can go out from the function with the absolute sign. And also, x plus y, the function value, is bounded by x function value and function value of y. And that is called the triangle inequality. Here, the sum of the two sides, the length of two sides, is always larger than or equal to the length of the third side. So that is a triangle. So it is a triangle inequality. Once these three conditions are satisfied, then the function is called norm or vector norm. The most common norms are p-norms and infinite norm or maximum norm. Here, maximum norm is taking maximum value in modulus. Here, two of frequently used p-norms are one norm and two norm. One norm is the summation of absolute values, and two norm is now square the sum and then take square root. The two norm is also called the Euclidean norm, and we often use just the double bar and ignoring these two. Once it is ignored, then in default is two norm. And one may consider the infinite norm as the limit of p norms. That means that here, limit, p goes to infinity of x. Now here, p norm is the same as now x of infinite norm. Okay, so the infinite norm can be considered as the limit of a p norm. We can check it quite easily. For example, now, we'll try to use only three components. So let's say x is in R3. Then x of p norm will be now, x1, p power plus x2, now p power plus here x3 power p and 1 over p, right? So assume x1 is the largest among these three values. Then as p increases, this whole thing inside this parenthesis, and that will be dominating. And for example, this is 2 and this is 1 and 1. Then later on, this one will become much larger than the other two. And assuming that x1 is the largest one, that is the largest one, then here we can write in this way. Now that one is, let's try to get x1. Now p norm can go out, and then this first one is 1, and then that is x2 p power over x1, now p power, plus again x3 power p over x1 power p, like that, and 1 over p, right? As p increases, and now this is the largest one, then it is converging to 0, because denominator is larger than numerator, so this ratio is less than 1. Power p makes that term goes to 0. So these two are converging to 0. right? And remainder part is exactly now x1 norm. So it become, it is converging to now x1 absolute value, right? So as p increases, now here it is converging to the maximum norm. In the beginning, we assumed that x1 is the largest one, so that it becomes here maximum norm, right? Okay. For metric norm, again, similarly, the norm requires these three conditions, and the function value of the metric must be non-negative. Once it is 0, then the metric must be 0. And lambda multiplication can go out with absolute sign, and also this triangle inequality must be satisfied. Once these three conditions are satisfied, then the function is a metric norm. I'm sorry. Okay, here Frobenius norm is defined in this way. For each component, the squared and summed n and 1/2 power. For every component, squared components will be added, and here square root will be taken. That is called Frobenius norm. Of course, this definition will satisfy these three conditions, so it is a norm. And here also, quite a convenient norm is induced metric norm. Okay, here a norm is maximum when x is non-zero for every vector x, non-zero vector. Here ax norm divided by x norm. Once a vector is multiplied to the metric, then this itself is a vector. So here, this vector norm over, of course, x is vector, so this vector norm, and among these values, for every possible x, non-zero x, we measure this quotient and try to get the maximum. That is definition of the metric norm. And in this case, this metric norm is defined from vector norm. So we call it induced metric norm or a subordinate norm, and sometimes it's called operator norm. Okay, here. Now, for all operator norms and the Frobenius norm, it is always true. And also, AB product norm is bounded by A norm and P norm. Now, A1 norm, this is operator norm induced from vector 1 norm, so that here 1 norm, metric 1 norm, is a maximum for non-zero x, ax1 norm divided by x1 norm. That is definition. Now, getting this value is not easy, but mathematically it's the same as this one. Here, the I summation, so the modulus absolute value of the entries will be added vertically. Okay, so let's see here. Metric is given in this way, so that modulus, absolute value of entries are added vertically. I summation means vertical summation. Then we have, for each column, we have a quantity. So among these values, maximum one will be A1 norm. So it's much easier to get one norm. Rather than this definition, you can get it by using this one. This one is for computation, mathematically the same. Okay, for a infinite norm, that is the definition. Ax infinite norm divided by x infinite norm for non-zero vectors and taken the maximum. That is the definition. But we can compute it by using this one. Okay, now for that one, J summation, so that absolute value will be summed horizontally. Then each row will make a number among these numbers, and we try to get maximum, that is a infinite norm. Okay, here A2 norm is now, that is definition. Now this is not simple. You have to get A transpose A, and for the matrix, you have to find eigenvalue. Among these eigenvalues, the largest one, so that first you have to find the eigenvalues of A transpose A and take the largest one and square root. And that is exactly A2 norm. It is not simple, however, it's better than that one. Okay. Now for one norm and infinite norm, here you can get it quite easily. This is a vertical summation, so one is vertical. Now this is horizontal summation. This infinity notation is somewhat horizontal, right? So that you cannot be confused. Okay. Now A2 norm is the same as A transpose 2 norm. For 2 norm, it's true. And here, once the matrix is normal matrix and satisfying this identity, this equation, then now 2 norm, A2 norm is just simply taking largest eigenvalue of A in modulus. And when A is symmetric, then automatically normal, so that the largest eigenvalue in modulus will be the 2 norm. Okay? The condition number of matrix, square matrix, can be defined in this way. Once it is invertible, then here A norm times A inverse norm is the condition number. Okay, here, let's see this example. A is given here, then we can have here A inverse and A transpose A. Now A1 norm, A infinite norm, and A2 norm. Okay, let's try to find them. A1 norm, okay. Now for 1 norm, we have to add vertically in the absolute value of entries. This is 2. This is now 8 and 5. So 8 is the largest one, so that A1 norm is 8. Right? How about A infinite norm? Horizontally, we are adding them 5, 5, 5, so that the maximum is 5. A2 norm. Now for A transpose A, we have to find the eigenvalue, and the largest eigenvalue will be used to get the A2 norm by taking square root. So you can find here eigenvalues and take the largest one and take square root. Okay, let's try to get L1 condition number. That means that now condition number is defined generally in this way, but here for matrix norm, is 1 norm is used, then that is now one norm condition number. So that is L1 condition number. K1A is by definition A one norm times here A inverse one norm. Okay? Okay, we already know A one norm is 8. Now A inverse is given here. Let's try to get one norm. One norm is gotten by adding the absolute values vertically. 15, 8, 15. So largest one is 15, and along with 120, 1 over 20, here 15 over 20 is the one norm of A inverse. So that's the L1 condition number. Condition number of a matrix is always larger than or equal to 1. And once condition number is large, then here, if you manipulate the matrix, then the larger condition number is, the larger error may propagate. So that, and here, large condition number matrices are not easy to deal with. Okay? Okay, that's the end of section 1.2. Thank you.